we're going to take a look at the next part of electrochemistry, which is oxidation states. Now, essentially, an oxidation state is the apparent net electrical charge that an atom would have if electron pairs in those covalent bonds belonged entirely to the more electronegative atom. Now, electronegativity does play a part in oxidation states and determining oxidation states. Now, essentially, if we picture a covalent bond or a compound that's sharing electrons, we see that there is generally there's one component that is more electronegative. Now, essentially, when we talk about electronegativity, we talk about how electrons migrate towards that more electronegative atom. Now, when we talk about oxidation state, what we're essentially referring to is we decide that instead of the electrons simply migrating towards the more electronegative atom, we're saying that those electrons belong to the more electronegative atom. Now, there's a couple other points that we need to consider. Metals and monoatomic anions tend to lose electrons. Okay, nonmetals and monoatomic cations tend to gain electrons. So what we would see here is something like this, where if I look at copper as an example, I see copper tends to form a cation and it loses electrons. Electrons are a product. Whereas if we look at something like a nonmetal, like oxygen, we see that it gains electrons and it turns into oxygen anions. Now, we have to always remember that if we lose electrons, this is oxidized. If we gain electrons, we're being reduced. So we can either use one of our two acronyms, which is OIL-RIG or LEO-GR. And again, either acronym you choose to use is completely acceptable. And it's just a great reminder to keep on jotting it down, having it at the top of your page as we go through. So let's take a look really to what this really means to have an oxidation state and having electrons belonging to a more electronegative atom. So oxidation state or oxidation number is essentially just a way of keeping track or counting electrons. Now, all atoms in an element have an oxidation number or state of 0. So that would be anything, for example, oxygen in its atomic state, copper in its atomic state, aluminum, sodium. Any of these examples could work as an atom in an element. So if you see an element, it's in its natural state, so oxygen gas or copper solid, etc., it has an oxidation number or an oxidation state of 0. Hydrogen in all compounds has an oxidation number of +1. Now we see that in all examples except for in hydrides. Now again, a hydride is a component or a compound, with hydrogen mixing with another metal, which is rare in terms of this course. Okay, oxygen we see has a oxidation number or an oxidation state of -2. Again, that's except for peroxides. Peroxides, we see that it has an oxidation number of -1. Okay, all monoatomic ions have a charge of its ion as its oxidation number. So, for example, if I have copper 2+, the oxidation number is in fact 2+. If I have sodium positive, the oxidation number is +1. If I have manganese 4+, again, it's my charge on my ion that states my oxidation number or my oxidation state. Now, essentially, when we're talking about electrochemistry, we're talking about the movement or transfer of electrons. So this is just a way of counting these electrons in order to keep track of where they're going in a chemical reaction. So a few more rules that we need to keep in mind is when we're determining an oxidation number or an oxidation state, we need to look at the sum of our oxidation numbers of any entity in that compound or polyatomic ion or whatever we're looking at, and that must equal the net charge on that entity. Okay, and it also only works, determining oxidation number only works if there's one unknown entity to solve for. So if I look at my example of methane, okay, which is CH4, I know from the previous slide, I'm just going to flick back here, I see that hydrogen has a +1 charge, or sorry, oxidation number, when I'm talking about any compound other than hydride. So I need to know that hydrogen has a +1 oxidation number and oxygen has a -2. Now, I would definitely have these 4 points written down and definitely be very familiar with hydrogen having a +1 and oxygen having a -2 in these examples. So just good to have it fresh on your brain so that we can get through some examples sort of quicker. So when I go back to my example here, I know that hydrogen, and the way that we solve these is just writing the oxidation numbers above the atoms in our compound. So I know hydrogen has an oxidation number of +1. So that means that I have one unknown. My unknown is carbon. And when I total up my entire oxidation numbers, they have to equal the net charge on methane. Well, methane has a net charge of 0. So when I look at my +1 oxidation number, I know that +1 is for one single hydrogen. When I look at my example, I see that there's 4 hydrogens. This means that I must have an oxidation number of +4 for all of the hydrogens. Now, in order to cancel out the +4, I need to have a -4. Pardon me. So I know that my charge or my oxidation number on carbon is -4. Now if I look at this more algebraically, and if you were a math person, you probably prefer this method rather than just kind of guessing or not guessing, but sort of looking at it in a logical manner here. If you want to really figure out where these numbers are coming from, let's take a look at where these numbers are coming from in an example. So I have 0 as my net charge. Now I'm just going to jot that down below here. That 0 represents my net charge on my entity. In this case, it's 0. Okay, once I do that, I'm going to have my net charge plus, because I need a net, my net charge equals X, which is my unknown. Okay, in this case, it's carbon. So this is my unknown. In this case, it's carbon. Okay, and I have X plus, this is because I need a net overall charge. So I have my carbon plus my 4 times my +1. Now that again is 4 hydrogens. This number represents the number of atoms, and this represents my oxidation number. So number of atoms, oxidation number. Okay, so what I see is that when I multiply this out, I see that 4 times +1 is +4. So I would get, and I would simplify this as 0 equals, 0. Oh yeah, we'll do that. We'll do an intermediate step. 0 equals X plus 4. And when we're solving for X, we need to do the opposite, equal and opposite to both sides. So I'm going to subtract 4 from this side. Those guys cancel out. So I have 0 minus 4. So minus 4 is equal to X. That is how I would solve this more algebraically. Now, if I look at a second example, again, I'm looking for an unknown. So if I look at my sodium sulfate, okay, I know for sure my oxidation state of oxygen is -2. However, I have 2 unknowns. So the one thing you also need to keep in mind, and maybe I would, if I was you, I would maybe put this down as an extra little note, is that ionic compounds dissociate. Okay, that's an important thing to consider. So when we talk about ionic compounds dissociating, then I can look at this example of sodium sulfate as sodium ions and sulfate ions. So I'm just going to erase this so I have a little bit of room here. So if you don't have this little example here written down with my methane and my algebraic solving of methane, you might want to do that now. But I'm going to erase it here so I have some space. Okay, so when I look at my example here of sodium sulfate, I actually dissociate it into sodium and sulfate. Now, I know that my oxidation state of my ions are always the charge on that ion. So I have sodium, which is a positive 1, and then I have my sulfate. So I no longer have my sodium as an unknown, but I do have my sulfur as an unknown to solve for. So I have to do this in the same manner that I have done the previous question. So I have a net charge of -2, and -2 equals x plus 4 times -2. So then I have -2 equals x plus -8. And when I simplify this further, again, anything I do to one side, I have to do to the other. In this case, I'm going to add 8 to cancel out these, in which case I'm going to add 8 to this side. -2 plus 8 means that x is equal to +6. Therefore, if I was to plug in +6 into my example for sulfur, I would see that +6 is my oxidation state for sulfur, and my oxidation state for oxygen is still -2, and there's 4 of them. So again, my net charge is equal to 2 negative. So I have -2 times 4, which is -8, plus 6, still resulting in a -2 overall charge. So now that you have the idea on kind of how to determine oxidation number, we're going to take a look at what this means in terms of a redox reaction. So if we're talking about oxidation number, we can see how electrons affect an entity in a redox reaction. Now, we see that if there are other atoms present that have a stronger electronegativity, there's the potential for those electrons to be pulled or moved between entities. So if the oxidation number of an atom or ion changes, okay, if it changes during a chemical reaction, then an electron transfer has occurred, or a redox reaction has occurred. So an increase in the oxidation number is an oxidation reaction. A decrease in the oxidation number is a reduction reaction. Now, the way that I like to think about that is if we have an increase in our oxidation number, okay, an increase meaning it's becoming more positive. If we're becoming more positive, I can never gain protons, but I can lose electrons. So because I'm becoming more positive, I'm losing electrons, which means I'm oxidizing. Okay, remember this is our oil component or our Leo component. Again, if I become more negative, again, I can gain electrons, so I'm gaining electrons, which means that I am, I've combined my sayings here. I am reducing, okay, or it's a reduction reaction. So keep that in mind. If I become more positive, I'm losing electrons. If I become more negative, I'm gaining electrons. So if I take a look at this example here, and I take a look at what happens to my oxidation number of all my compounds, I can gain an understanding of the component that is being oxidized or reduced if any of that is going on. So in this example, I have an oxidation state of carbon, and because this is solid carbon, the oxidation state of an atom is 0. There is no charge on that atom, so it is carbon in its solid form. Now, my oxygen in this case is also 0 because it's oxygen gas. It's oxygen O2, which is oxygen in its purest form. Okay, when I look at carbon dioxide, I know that this is a compound, so I know that I have oxygen with an oxidation number of -2. Now remember that we have to go -2 times 2, which is -4, and I have a net charge of 0, which means that I need a +4 on my carbon. Now, when I go through this algebraically, again, I would say that 0, when I'm determining my carbon here, 0 equals x plus 2 times -2, which means 0 equals x plus -4. I'm going to add 4 to cancel those entities out, so x equals +4. Okay, so what I see here is carbon initially goes from 0 to +4, and I always write it like this, and oxygen goes from 0 to -2. Now, carbon becomes more positive. Now, because carbon became more positive, it is losing electrons. It's lost electrons. Now, we know, and I'm just going to jot this down up in my top corner here, we know our oil rig. Now, when I am losing electrons, I'm being oxidized. And I'm just going to abbreviate that as ox. Okay, so it's oxidation. And when oxygen goes from 0 to -2, I see that it's gained electrons, which means that it's being reduced. So this is reduction, and I'm just going to abbreviate that with red. So I have a redox reaction here. When I look at my example below, again, I see, and sorry, I should have included my states of matter here. This would be solid, aqueous, and a gas. And I'll just continue that here. Okay. So when I take a look at my zinc solid, I know again zinc solid is an atom. So it's an atom as an element, therefore it has an oxidation number of 0. When I look at hydrogen, hydrogen has, it's in its ionic form. So I either know that it's a +1 based on its charge here, or I just know that hydrogen has a +1 oxidation number. Zinc has a 2 positive oxidation number because it's in a monoatomic ion, and that just has the charge of whatever that ion is, and hydrogen gas, which is again an element, it's in its atomic form, therefore it has an oxidation number of 0. So when I take a look at this example, I see that zinc goes from 0 to +2, where hydrogen goes from +1 to 0. Again, we go from 0 to +2, which means we've lost electrons or oxidized. And we see that we have +1 to 0, which means we've gained electrons. We've become more negative. So if we've gained electrons, we're being reduced. Okay, so we can identify these reactions as reduction and oxidation half reactions. If we take a look at our last example here, we see that we have hydrogen, again, +1. +1 times 4 is +4, which means that this has to be -4. Okay, oxygen gas is a 0. Oxygen in this compound is -2. -2 times 2 is +4. Okay, and we see in water that we have a -2 and a +1. So again, let's take a look at what we have here. Carbon goes from -4 to +4. Okay, And we see that oxygen goes from 0 to -2. However, we see oxygen in two different compounds. We see it in our carbon dioxide as well as we see it in our water. Now, this is something that you may see and it may come up, and it is totally fine. We have our carbon to our carbon goes from -4 to +4, which means it's becoming more positive, which means it's losing electrons, which means this is oxidation. And we see oxygen going from 0 to -2 and -2. Regardless of how many times this shows up, we see that it is gaining electrons, which means that oxygen is being reduced, or reduction equation. Okay, we're only looking again in our change from our reactant to a product, so we say that oxygen is reduced, and it doesn't matter where that oxygen is reduced in our products. Okay. Now, we can see that we can look at the number of electrons transferred, which can tell us a lot about a chemical reaction. So from oxidation numbers, we can actually see that we can balance redox equations or reactions using oxidation numbers. So the way that we do that is the total number of electrons gained by one entity must be equal to the total number of electrons lost by another entity. So if we take a look at an example, I'm going to explain how you solve this, and I might pull up a separate page here to show you the work as I go through these examples, because I might need a little bit of space here. But you'll start to get an understanding as how important this electron transfer is. Always, 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 we need to have the same number of electrons transferred from one entity to another. So if I open up another page here, we'll take a look at the first example. Okay, so we have H2S plus oxygen gas gives us sulfur dioxide and water. Now, when I take a look at this, I'm just going to rewrite our example out here on the side. So we have okay. So here's my example. It's in a neutral solution, so we can just slide this over here so I have a little bit more room. So we have H2S and oxygen gives us SO2 and H2O. So when I assign my oxidation numbers, just get a different color here, I have hydrogen being a +1. Now because I have +1, I have two of them. This means that sulfur has to be a -2. Oxygen gas, because it's an atom, it's in its elemental form, has a 0 oxidation number. In a compound, it is a -2, meaning that I have -2 times 2, which is -4, net charge of 0, so this has to be +4, and I have -2 and +1. So what I see here is that I see that sulfur goes from a -2 to a +4. So -2 to +4 means it's losing electrons. If it's losing electrons, this is oxidation. Okay, and I see that oxygen goes from 0 to -2 and to -2. Again, it doesn't matter if this shows up twice. However, I see that I'm gaining electrons, which means I'm reduced. Okay, so when we take a look at this overall reaction, we can get an idea of how many electrons were moved. So I'm going to rewrite out my equation and sort of make it a little bit more simplified here. So I have H2S, space it out a little bit, Here we go. So I always look at my reactants, so my H2S and my O2. And what I see is, because I'm looking at my entire compound, I am looking at the entire thing, but I use my sulfur change in oxidation number to determine the number of electrons that were moved from that entire entity. So when I look at this, I see that sulfur goes from -2 to +4. So if I think about this as a number line, again, I have -2 to +4. Okay, and I think again, number line, that goes -2, -1, 0, 1, 2, 3, and then 4. So that's a difference of 6 electrons. Okay, when I look at my oxygen, from 0 to -2, that is 2 electrons. Okay, the thing that throws us a little bit for a loop is that we see that 2 times. So let's take a look at how we deal with this. When I record this, I write down how many electrons were transferred per atom. So in this case, we have 6 electrons per sulfur. Now, because I only have 1 sulfur in this compound, I'm going to go 1 times 6 electrons per H2S. This tells me that we have 6 electrons transferred per H2S, and that's 6 electrons for sulfur. Okay, when I take a look at my oxygen, I see that there was 2 electrons transferred, so 2 electrons per oxygen. Now, I have 2 oxygen atoms, so I have 2 times my 2 electrons, so then that equals 4 electrons per O2. So I see that I have 6 electrons and 4 electrons being transferred. Well, the one thing we know that is super duper important is that we have balanced number of electrons being transferred. We have to have the same number of electrons gained as we do lost. So when I take a look at this, I can think of a coefficient that I could use to balance these two numbers. So I would say our common sort of coefficient would be 12, which means that I would multiply this by 2, and I would multiply this by 3 in order to get 12 electrons total transferred. Now, these numbers here in green equal our coefficients when we balance our chemical equation. So what that means is I need 2 H2S and I need 3 O2s in order to start this balancing process. Now, once I've taken a look at my reactants and balancing the electrons that were transferred there, I can complete my balancing using those coefficients. So I have 4 hydrogens on my reactant side, which means I need 4 hydrogens on my product side. By adding a 2 here as a coefficient, I have 4 hydrogens. Okay, and when I take a look at oxygens, I have 6 oxygens, which maybe I'll balance my oxygens at the end because I have them in 2 components. But let's take a look at sulfurs. Again, 2 sulfurs, and I have 1 sulfur here. So if I put a 2 in front of this guy, I balance my sulfurs. Now let's double check my oxygens. I have 6. I have 2 times 2, which is 4, and 2 times 1, which is 2. 4 plus 2 is 6. Therefore, this is my balanced chemical equation. Now, I can balance a variety of chemical equations using this method of my oxidation number. And again, the steps are to look at which entity is oxidized, which entity is reduced, then figure out how many electrons were transferred per atom, and then multiply that by how many atoms were present. That will give you your coefficients, that will give you how many electrons were transferred, which then you find a common denominator to determine your coefficients that you'll use to balance your chemical reaction. Okay, so we know that sometimes reactions are not always in a neutral solution. So let's take a look at an example where we have an acidic solution. So our example is our chlorate ion plus our iodine goes to chlorine and iodate. Now let's rewrite this out here as our chemical reaction. So I have, actually I'm just going to give myself a little bit more room, my chlorate, it's aqueous, plus my iodine, giving my chlorine, and my iodate. Okay, so when we take a look at figuring out our oxidation states here, all right, I have my chlorine and my oxygen. I have a -2 on my oxygen. Now, because I have a -2 times 3, that's a -6 overall charge. Now, I have to remember, a -6 oxidation value for my oxygens, but I have to remember I have a net charge of -1. So I go -2 times 3 is -6, which means I need a +5 to result in a net charge of -1. When I look at iodine, I see that it's in its elemental form, which means that it has an oxidation state of 0. Chlorine has an oxidation state of -1 because it is simply the charge on that ion. And when I look at iodate, I see that oxygen again has a -2. -2 times 3 again is -6, net charge of -1, also resulting in a +5 oxidation state. So again, what I see here is chlorine goes from +5 to -1, and iodine goes from 0 to +5. So again, if we see +5 to -1, we become more negative, which means we've gained electrons, which means we're reduced. We go from 0 to +5, which means we've lost electrons, becoming more negative, which is oxidized. Okay, so when I take a look at this example, I see that from chlorine to chlorine, we've had a difference of 6 electrons. So I see that there's 6 electrons per chlorine, and I only have 1 chlorine atom. So that means I have 6 electrons per chlorate. Okay, so again, this would be 6 times 1, and I'm just not recording that mathematical function in this example. Okay, now when I look at iodine, I see 0 to +5. That means that there's been 5 electrons per iodine. And I see that I have 2 iodines, okay, because I have 2 atoms. So that means I have to go 5 times 2, which is 10 electrons per iodine atom, okay, or per iodine in its natural elemental state. Now, when I take a look at this, again, I would say my common denominator between the two of these is 30. So I'd go 6 times 5, which gives me my coefficient, and I have 3 times 10, so I'm going to have times by 3 to give me my common denominator of 30. Now, the one thing we need to keep in mind is that this is in an acidic solution. So one thing we need to write down maybe is that it's in acidic solution. Okay, so I can continue on the same way from my previous example and record these values as 5 and 3. Okay, from there I can continue to balance the rest of my equation. So I have 5 Cl's, I need to have 5 chlorines on this side, and I have 6 iodines, which means I need to have 6 iodines on this side. So when I go back and check my oxygens, I see that I have 5 times 3, which is 15 on my reactant side, and I have 6 times 3, which is 18 on my product side. So all of a sudden something hasn't quite worked out. So this is where this acidic solution comes in to be very important. Okay, we know it's a solution. I have all my components as aqueous in this solution. And in the example, it said that it was acidic. So I'm just going to rewrite out this equation with its balance with what we have so far, and we'll take a look at how we continue on with this. So I have 5 chlorates, 5 chlorines, and 6 iodines. Now again, everything is balanced except for our oxygens in this example. So the same way that we've balanced our other equations previously in the unit by adding oxygens and then followed by adding hydrogens, okay, I can do that in the same manner. Now I can't simply just add oxygens. If you remember, I have to add oxygens in the form of water. So again, on my reactant side, I have 15 oxygens. On my product side, I have 18 oxygens, which means I need to add 3 oxygens in the form of a water molecule. Okay, so I have 3 water molecules on my reactant side. Now again, I didn't have any hydrogens present, but now I've added 6 hydrogens, so I have to include my 6 hydrogens on my product side to balance out my hydrogens. Again, I can double check my work by going through again, checking my atoms to make sure my atoms are all balanced, and I see that I have balanced everything. My chlorines and my iodines and my oxygens and hydrogens are both balanced, are all balanced on both sides. And what I need to just ensure is I also need to double check my charge. So on my reactant side, I have 5 times a negative, which means I have a negative 5 net charge on my reactant side. And on my product side, I have 6 times negative 1, which is negative 6, plus 6 times positive 1, which is positive 6. So those two entities cancel out in terms of charge. And then I have 5 times this negative 1, meaning I have a negative 5 charge, net charge on my product side. So they each have a negative 5 net charge, which means that this is then a balanced chemical reaction. And we've done that balancing using our oxidation states. Now, if we take a look at a basic solution, let's take a look at my example here. There we go. And I take a look at my example here. I see that I have my methanol plus my permanganate, and I get my carbonate ions and my permanganate ions as a product here. Okay, so I'm again have this in a basic solution, so I'm going to take a look at my example here. And I'm just going to rewrite this out just because it is a little bit simpler. So again, I have my methanol, I have my permanganate, and this turns into my carbonate. Okay. Now, again, I have to start by assigning my oxidation numbers. So I have a negative 2, a positive 1, and a positive 1. Now, this example is a little bit trickier. I have a few more entities to consider when I'm determining my unknown. So I have positive 1 times 3, which is positive 3, plus another positive 1, which is positive 4. And I have a negative 2. Well, my net charge is 0. So I know that if I have another additional negative 2, that means that I have negative 4 total and positive 4 total, which balances it out. When I look at my permanganate, okay, I see negative 2. Negative 2 times by 4 is negative 8. I need a net resulting charge of a negative 1, which means I want 1 left over, which means that if I have a positive 7, that means that I would have 1 negative left over. Continuing on, negative 2. Negative 2 times 3 is negative 6. I want a 2 charge of negative 2 resulting, which means that I want to have a positive 4 on my carbon. Again, minus 2. Minus 2 times 4 is negative 8, positive 6 to cancel out to remain with a negative 2 charge left over. Again, we take a look at what is oxidized, what's reduced. I see that my carbon goes from negative 2 to positive 4, and I see that my manganese goes from positive 7 to positive 6. So if I've become more positive, I've lost electrons, this is oxidized. And when I go from positive 7 to positive 6, I've gained electrons, so this is reduction. Now if I take a look at the number of electrons transferred, from negative 2 to positive 4, again that's 6 electrons per carbon. Now in my compound here, in my methanol, I only have 1 carbon present, so this is 6 electrons per methanol. Okay, when I take a look at the difference here, I see that 1 electron is transferred per manganese from 7 to 6. Okay, and I have 1 electron transferred per permanganate. Again, that's only because I have 1 manganese present in this polyatomic ion, meaning that I just need to consider 1 electron. Now when I take a look at how I would balance these, the common denominator would be 6, so I multiply this by 1 and I multiply this by 6. So again, I put a 1 here, a 6 here. Okay, I continue with my balancing, which means I need to have 6 manganese on my other side here. I have 1 carbon on each side, which sort of balances this out. Now let's keep in mind that I'll just jot the ones down there so we keep that fresh in our mind. Now, because this is a basic solution, we continue to our steps that we have done in our previous examples. Now, just a reminder, when we have a basic solution, we consider it to be similar to an acidic solution in terms of the steps, and then once we do that, we can balance out the charge and we can cancel out our acidic nature by adding hydroxide ions. So, the first step is once we've gotten this far, we need to add our oxygens in the form of a water molecule. So I have 1 oxygen plus 24. So I have 25 oxygens on my reactant side, and I have 3 plus 24. So I have 27 oxygens on my product side. So what I need to do is I need to add in, and I might just try and sneak this in here at the top. No, I won't. I will run out of room here. So I need to add my 2 oxygens, okay, because again I had 25 on this side, pardon me, and 27 on this side. So I need to add 2 oxygens in the form of water. So I have 2 H2Os plus my 1 methanol plus my 6 permanganate which forms my carbonate, plus my 6 of these guys. And once I've added these hydrogens, I need to also balance out the total number of hydrogens on either side. So I follow that up by saying I have 4 hydrogens, but I cannot forget that I also have hydrogens in my methanol. So I have 4 hydrogens plus an additional 4 in methanol, meaning that I have 8 total hydrogens on my reactant side, meaning I have to add in 8 total hydrogens on my product side. Okay, when I do that, I've balanced my hydrogens now, but because this isn't a basic solution, I need to add in my hydroxide ions. Now, the way that I do this again is by adding in as many hydroxide ions to the side with the extra hydrogens to cancel out to turn them into waters. So that forms 8 H2Os. Whatever I do when I add hydroxide, I always have to add my hydroxide to my other side as well, meaning that I have to add, and in the equivalent amount, so I have to add 8 hydroxides on my reactant side. Now, when I write out my entire sort of balanced reaction here, I see that I have 8 hydroxide plus I cancel out my 2 waters on this side, which results in 6 waters on this side, but we'll get to that. These guys I'll just put a line through for now. Plus my methanol plus my permanganate. And that forms my carbonate. Oops. There we go. And my 6 remaining waters. There we go. So that should be my net reaction that I've balanced using my oxidation states as well as a combination of my knowledge of how I balance chemical reactions with my basic formulas. So again, if you need to go back and rewind at any point here, I would suggest doing that now. So let's go back to this page here. So that's a good way to look at how we balance redox reactions using our oxidation numbers. So that wraps up this sort of mini lesson on oxidation numbers. At any point that you need to go back and rewind to understand oxidation numbers or solve these problems using the algebraic method, you can do that now. Now, I do have some assignments that's lined up for you. So if you need to go back, do that now, and good luck.